We're now going to kind of put everything all together and discuss quarks and the standard model and kind of look at the current picture of where things are at. To start out with, we'll look at this table that we've seen over and over again. And here we had kind of three categories. We had the gauge bosons that carried the forces, we had these 6 leptons, and then down here we had the hadrons, which broke up into mesons and baryons. And the key word here is selected. This is only a few. There are over 100 of these things, and so we sometimes call this the particle zoo, because for a while there they were discovering new particles all the time, and it was kind of hard to keep track of all of it. And that's kind of a distinct picture, a different picture from what we have up here. Here we've got 6 leptons and just a handful of force-carrying particles. So why do we have this nice kind of organized, minimal number of particles up here, and then we just have all kinds of junk down here? Well, some physicists figured maybe we can simplify things a bit. And there was some evidence that these particles here, these hadrons, were not actually fundamental or elementary. They were made of other smaller particles themselves. Not so with these particles up here. So we think that these are the smallest they get. They're not made of constituent particles. But these guys down here, in 1963, we proposed, a guy named Murray Gell-Mann proposed a theory of quarks. And he said that all of those hadrons are actually combinations of just 6 particles known as quarks. Actually, he didn't originally propose 6. He originally proposed 3, I believe. But yeah, up, down, and strange were the first 3 that he thought would kind of account for everything, and later we added a few others. But this makes things pretty nice. We just have 6 of these, 6 leptons, and then the force particles, and we're good to go. Along with these other quarks came some other properties. We looked at strangeness in the last video. I might have mentioned charm. There's also bottomness and topness to go along with the bottom quark and the top quark. Now you notice the strange quark has a -1 strangeness value, and the bottom quark has a bottomness value of -1, and the others have positive values for their respective categories. The antiparticles, there are antiparticles for each of these, as you would probably guess, the anti-up, anti-down, and so forth. And then you just switch the sign on these strangeness, charm, bottomness, and topness quantities. Now it did do some weird things with these quantities here. It turns out that the quarks have fractional charges, which at first seems kind of weird, but then if we realize that the reason why we called a proton +1 and an electron -1 is because we thought those were the smallest charges you can get. So the only thing that happened is we found that there were smaller charges, and we didn't want to rename all the chemistry and stuff we had going on with positive and negative charged protons and electrons. I mean, if we'd found this first, then we probably would have called the strange quark -1 and the up quark +2, and then protons would be just +3 and electrons -3, and everything could have worked out okay. Baryon numbers, same thing, where we have fractional baryon numbers, but we always add up to get whole number baryon numbers in the end. So how do these things combine? Actually, I think we're going to talk about the name here. So the name quark, Gell-Mann actually borrowed it from a work by James Joyce called Finnegan's Wake. What is this strange symbol here? I don't know. Don't worry about it. Anyway, part of this work says 3 quarks for muster mark. Sure, he hasn't got much of a bark, and sure, any he has, it's all beside the mark. Anyway, he was looking for a word, and he just really liked this quark word. What it exactly means, I'm not sure. And there's some debate over whether it's pronounced quark or quark, and if you want to get into some of the details, Gell-Mann himself, he wanted it to be pronounced quark, but he kind of explains how you could maybe take it to be quark in certain circumstances, depending on how you interpret that poem and whatnot. Anyway, if you want to pause it and read through that, feel free. If not, it's not something that you need to know, at least not for the test. I mean, it's a good piece of trivia, I guess. All right, so how do these quarks, which is kind of the more common pronunciation, how do these combine to give us all of those hadrons? Well, there's two options. For the baryons, over here, baryons, they always combine in threes, and they combine in groups of either all normal quarks or all anti-quarks. And so here you've got a proton. It's made of 2 up quarks and a down quark, and a neutron is made of 2 downs and an up. Over here we've got the mesons, and the mesons are always made of just 2 quarks, but one is always a regular quark and the other is an anti-quark every single time. So quark-anti-quark pair, whereas these are 3 quarks or 3 anti-quarks. And if you notice these charges, if you add them up, you've got 2/3 plus 2/3, which is 4/3, minus 1/3 gives you 3/3, so it sums up to a charge of +1. For the neutron, you've got 2/3 minus 1/3 minus 1/3, and this sums to 0. So all of the properties of the hadrons can be derived from the properties of the quarks from which they're made. Here you're going to have 2/3 plus 1/3, and so you'd get a positive charge for this pion and negative charge for that one, and so forth. Now you might have noticed that they have colors here. Oh, by the way, the different quarks, we call them different flavors of quarks. We use that same term for the different types of neutrinos as well, but they also talk about quark flavor. Ooh, red thing, don't know where that came from. Alright, so you notice that these have different colors here. You've got a red, a green, and a blue, and if you're familiar with adding colors, not pigments, but colors, these are the primary colors, and you add them together and you get white. And so this is known as quantum chromodynamics, or QCD, quantum chromodynamics, which is just a fancy word for using colors. And there's another rule that says the colors of the quarks always have to add up to give you white. And you know, if you have red, green, and blue, you get white light. And each type of quark doesn't always have to be the same color. Obviously, there's a red down quark here and a blue one right there. But together you have to have one of each. Over here you're going to have a quark that's a given color, and then the anti-quark has to be that anti-color. So if this guy's blue, this guy's anti-blue. Now we can't really change the color to anti-blue, so typically they use yellow. I don't know why, but if you have an anti-color and a color adding up, then you get white again. Okay, but this idea of quantum chromodynamics and color has become pretty fundamental, and so often instead of calling it the strong force, they will call it the color force, and they'll refer to color charge. So this kind of it's an analogy to electric charge, right? So you've got electric charge that gives you the electric force. You've got electromagnetic force. You've got color charge that gives you the color force or the strong force. And then you've got mass that gives you gravity, and for the weak force they call it weak charge. They didn't get as creative with that one. So there's quantum chromodynamics for you. Alright, so let's look at a list of some other hadrons, just to give you more tables, because I'm sure you haven't had enough. And here we're listing some of the other properties that we've just added: charm and bottomness. And so these different mesons and baryons have these new properties. You get all kinds of new names. This is called the J psi, and this is the D. A lot of times the subscript on these refers to these properties here. So the D, this is known as the strange D, the positive strange D meson. This has a C here because it's the charm sigma. So more fun things to add to all of our particle considerations. So let's look briefly at how we're going to apply these types of things. So let's say I've got 3 quarks, an up, down, and a down. We already kind of saw what this was, but if we didn't know, we could figure it out just by adding up the properties and then looking on these tables to see what properties match. So let's start out with charge. So I've got an up quark, and I go down here, and so that's positive 2/3, and then I've got a down, which is negative 1/3, and another down, so another negative 1/3. So whatever particle this is, it's got to have 0 charge. Also, I know it's a baryon because it's got 3 quarks, so I know that right off the bat. And we can look at baryon number, but I kind of know it's a baryon. It's going to have a baryon number of 1. And then the up and down, they don't have any strangeness, charm, bottomness, or topness, so all of those things are going to equal 0. And so if I go back, actually I'd have to run all the way back to the first slide, and I don't want to do that. So the only baryon that has no charge and no strangeness, charm, bottomness, or topness is the neutron. So we could figure that out just kind of by looking at these different properties here. All right, here's one we don't know yet, so a little more suspense for this one. We've got a bottom quark and an anti-up quark. So let's go ahead and start with charge again. The bottom quark over here has a charge of negative 1/3, and then the up quark, the regular up quark, has a charge of positive 2/3, and so this is going to be negative 2/3. By the way, the actual particles, the hadrons, never have fractional charges. So if you're adding up the charges of the constituent quarks and you get some fraction, you know you messed up somewhere. They always come out to be whole numbers. Also I forgot to mention, we don't ever see quarks by themselves. You know, as hard as we try to smash things together, we have never succeeded in getting a free quark all by itself. There is some other evidence that those quarks are in there, even though we don't see them directly, as opposed to you know, with an electron, we don't have evidence that there's other particles lurking inside the electron. We think the strong force is just so strong that we're not able to free those quarks off of the groupings of the quarks. Alright, so we add this up and we get a charge of negative 1 for this thing. Baryon number, well, the baryon number for any regular particle is going to be 1/3, or regular quark, and then the anti-quark is going to be negative 1/3. So we get a baryon number of 0, but we already knew it wasn't a baryon, right? Because we've got a quark-anti-quark pair, so we know that that has got to be a meson. And then let's see, bottom quark has bottomness, and we come over here and it's actually the regular one has a bottomness of negative 1. I'm going to use lowercase b for bottomness, so that's negative 1. The up quark doesn't have strangeness, charm, bottomness, or topness, so this is what we've got here. And if we go and look this up on a table, this works out to be the negative b meson. So it's the only one that would fit these quantities. If you don't believe me, I guess we could have gone and looked at that chart. So if we go over here, we're looking for a bottomness of negative 1, so that reduces it to these 3 here. We've got a baryon number of 0, so this guy is out of the race, so we narrowed it down to these 2 B mesons. And we've got a negative charge, so that narrows it down to this guy. And there you have it. That's how you do it. Alright, now if we kind of put all of this picture together, now we kind of have a fairly simple description of matter on the most fundamental level that we are aware of. Now, we could, with even more energetic particle accelerators, discover something new, and there's definitely strange things going on with dark matter. We're not really sure how that interacts with regular matter, but it does interact, at least gravitationally. So this might not be the final picture, but at this point it's pretty good. We made some good progress. We've got 6 quarks up here, and then we've got the 6 leptons down here, and then we've got the gauge bosons. And also recently, just a few years ago, we discovered the Higgs boson, which we will talk about more in class. You could add to this list the graviton, which has not been discovered yet, but we think it will be. It's an interesting massless particle. We think it has a spin of 2. We didn't really talk about spin. That's just another property that these particles tend to have. So this picture here as well as kind of the explanation of how these things work together, is known as the standard model of particle physics. It's basically, this is our best guess of what we know. I don't know if it shows up too well, but kind of the other nice thing on this diagram is in the background you can kind of see this outline here linking these particles over here with the force particles. So for these W and Z bosons, it links with everything, because everything feels the weak force. And then you've got the photon here links with these charged particles, and then you've got the gluon, which just links with these guys. Well, there you have it. There's our picture of matter at the most fundamental level that we currently know of. Congratulations on your newfound knowledge.